Welcome to Visual Algebra Lecture 3.9, Conjugate Elements. We've seen how conjugation defines an equivalence relation on the set of subgroups of a group. It also defines an equivalence relation on the set of elements. A central theme in mathematics is that things that are conjugate have the same structure. Conjugate matrices have the same eigenvalues and thus the same trace and determinant. And they even represent the same linear map but under a change of basis. Conjugate subgroups are isomorphic, but not all isomorphic subgroups are conjugate. Conjugate elements have the same order, but not all elements of the same order are conjugate. We'll explore conjugacy classes in the dihedral groups and the symmetric groups in this lecture, and we'll understand what it really means to say that two elements in a group have the same structure. Well, at least through the lens of conjugation. We'll see a different view when we get to automorphisms in the next chapter. We've seen how conjugation defines an equivalence relation on the set of subgroups of G. The equivalence class containing a subgroup H is called its conjugacy class, denoted CL sub G of H. We can also conjugate elements. Given an arbitrary element little h in G, we may ask which elements can be written as x, h, x inverse for some x in G. Here's a definition. The conjugacy class of an element, little h, in G, is the set. I'm going to use the same notation, just put an element here instead of a subgroup, and it's a set of all products of the form x, h, x inverse, where x is an arbitrary element in G. The first basic property, I'll call it proposition, but it's more of an observation, is that the conjugacy class of an element has size 1 if and only if that element is central. Let's prove this for good measure. So the conjugacy class of the element h has size 1 if and only if the conjugacy class of h is just h itself, because every element is conjugate to itself. Just take the identity. Well, what that means is that x, h, x inverse is equal to h for all x in G. Every conjugate of h is equal to h. Well, that's the same thing as saying that x, h equals hx for all x in G, and that's the same thing as saying that h is central. We take a random element x and notice that xh equals hx. And that's the end of the proof. It's elementary to show that conjugacy of elements, just like conjugacy of subgroups, is an equivalence relation. Remember, to verify this, we have to show the three properties of being an equivalence relation. We have to show that each element is conjugate to itself, and that just holds because E inverse equals h. We need to show that if G is conjugate to h, then h is conjugate to G. This is just like for subgroups. Suppose A inverse equals A, then I claim that if you take this and you multiply on the left by A inverse and the right by A, then we can get that A inverse H A equals G. So if A takes G to H, then A inverse takes H to G. And then for transitivity, if G is conjugate to H, say that A inverse equals H, and say that B inverse equals K, then I claim that if we take G and we conjugate by A and then by B, so this is just BA, G, BA inverse, we get K. And I'll let you check the details of that. As with any equivalence relation, the set on which it's defined is naturally partitioned into equivalence classes, where two things are in the same equivalence class if they are equivalent. In this case, that means they're conjugate. There's a theorem called sometimes the class equation, which I don't really think deserves this name. I think it's an immediate corollary of the fact that conjugacy is an equivalence relation and the fact that central elements are in size 1 conjugacy classes. But this says that for any finite group G, the size of the group is equal to the size of the center plus the size of the distinct conjugacy classes of size greater than 1. Why is this true? Well, the equivalence classes, or conjugacy classes, partition the group. In the center, these are the ones that of size 1. So if we add those up separately, we get the size of the center. And then what's left over are the equivalence classes, or conjugacy classes of size bigger than 1. Next, every normal subgroup is the union of conjugacy classes. What does this really mean? Well, it says that if we have an element, let's call it little n, in a normal subgroup, big N, then every conjugate of that is going to remain within N as well. That's all that means. So if an element is in a normal subgroup, then its entire conjugacy class is. So if N is in the normal subgroup, then Xn X inverse has to be in Xn X inverse, X big N X inverse. But since N is normal, this has to be N. And that means that every conjugate of little n is in the subgroup big N. So this means that the entire conjugacy class is contained in big N. And that's the end of the proof. Let's now look at the quaternion group, all of whose subgroups are normal. And let's partition it into conjugacy classes. And I'm not going to actually compute any conjugations, which is the brute force way to do it. So let's take this subgroup, which is normal, generated by I, and we know that I is not central because the center is just plus or minus 1. That means that the conjugacy class containing I has to have size bigger than 1, so 2 or more. But we also know that this subgroup generated by I of size 4 is a union of conjugacy classes. So here's what we have. In other words, we have these 4 elements in the subgroup generated by I. One of them is 1, one of them is -1, one's I, and one's negative I. And we're saying, well, these two have to be in their own conjugacy class because they're central. And we know that I must be in a conjugacy class of size bigger than 1. But there's only one other potential buddy, negative I. So without doing any work, we can conclude that indeed these have to be conjugate as well. Similarly, we can conclude that the conjugacy class of J contains plus or minus J, and the conjugacy class of K contains plus or minus K. We can use the same argument by just replacing this I with a J or a K. Here is the partition of Q8 into conjugacy classes. Notice that the center consists of the union of the 2 singleton conjugacy classes, then everything else has size 2. Here's a cycle graph of Q8. Again, I still like to draw these or color these nodes so you can see the orbits, but this just says that every element that's not 1 or -1 is conjugate to its negative and nothing else. Okay, let's touch back upon a subject that I mentioned in the opening monologue, which is that conjugation preserves structure. Now let's think back to linear algebra. Matrices A and B are similar, which just means conjugate, if A equals P, B, P inverse for some invertible matrix P. Conjugate matrices have the same eigenvalues, trace, and determinant. In fact, they represent the same linear map, but under a change of basis. As I said earlier, a central theme in mathematics is that 2 things that are conjugate have the same structure. And we'll explore what that means and entails in the rest of this lecture. First, let's start with the basic property preserved by conjugation, and that is that conjugate elements in a group have the same order. To prove this, let's consider an element G, which is equal to, let's say, x, h, x inverse in a group G. So x and h are conjugate. And let's suppose that h, the order of h, is equal to n. So what that means is that h to the n is equal to the identity, and n is minimal for which that happens. So here's what I claim. I claim that g to the n is the identity as well. So g to the n is x, h, x inverse to the n, and that's just x, h, x inverse done n times. So x, h, x inverse up to x, h, x inverse. You see what happens? Well, these consecutive x inverse h's are just the identity. So these all cancel, and we get h times h. So we get, at the end of the day, x, h to the n, x inverse. And with the assumption that x has order n, that means that x, this is x e times x inverse, which is just equal to the identity. So in other words, if two things are conjugate, so if g is conjugate to h, then we can say that the order of g, we can't here necessarily say that the order of g is equal to the order of h. We just know that the order of g, so if n is the minimal thing that when you raise h to, you get the identity, we just know that g to the n is equal to the identity as well. But maybe n's not minimal. So this says that the order of g is less than or equal to the order of h. However, we know that conjugation is an equivalence relation. So if we just reverse the order of this, we can get that h equals x inverse gx, and we can carry out the same proof and get that the order of h is less than or equal to the order of g. Now, this, I should say, is, I'm assuming the case that the order is finite. So I should say this is if the order is finite. And I'll leave it as an exercise to check that if the order of one of these is infinite, then the order of the other one is as well. And that actually follows right away. It's more, how do you write that up, in an elegant way? Because if the order of one of these is infinite, the other order is finite, you can run this argument and you can come up with a contradiction. To understand what we really mean by conjugation of preserved structure, let's revisit frieze groups, and in particular the frieze that emits every possible symmetry. Let's fix a central axis, L0, and let H denote the reflection across that. Notice that all of the so-called even axes look just like the central axis. If you squint your eyes, you can't tell the difference. So suppose that we want to reflect across a different one of these, say L minus 2. How do we do that? Using the generators. Well, we can translate to the right, that is, apply T to bring those diamonds to the central position. Then we apply our reflection, and then we just have to translate them back to where they came from. So we apply T inverse. And the net effect here is that we have just reflected across a different axis. Algebraically, this means that H negative 2, that reflection from here to here, is T H T inverse. Similarly, we can reflect across this axis, L minus 4, by doing T squared H T minus 2. And we can, from over here, we can do T to the minus 1 H T. So reflections across all of the even axes are conjugate. They have the same structure. They're basically the same up to relabeling. However, the other reflections, the ones across the odd axes, are fundamentally different. They don't go through diamonds at all. Now, each of these is still a symmetry. You can reflect across L minus 1, but you cannot relate it to the reflection across the central axis in the same way. If you were to do that, you would have to translate this by a half step, and that's not a symmetry. That sends diamonds to not diamonds. So fundamentally, the odd reflections are all conjugate because they have the same structure, as are the even reflections. And you can do a similar thing to compare the so-called even rotations about points that intersect diamonds versus the odd rotation. These are 180 rotations about the points that do not. The dihedral group, dn, is like a finite version of a previous frieze group. Not the frieze group that we just saw. It's a finite version of a frieze group that looks like this, or one that looks like this, for example. So in particular, dn is generated by r and f, where r to the n is the identity, f squared is the identity, and then frf equals r to the minus 1. Now, the frieze group, d infinity, is the same thing, but we don't have r to the n equals 1. So we have f squared is the identity, and frf equals r to the minus 1. Recall that from chapter 1 and from chapter 2. Just like how there were two types of reflections in a frieze, ones that went through the diamonds and ones that did not. For this frieze here, we could similarly say that we could declare this to be a central axis, and these are the one type of reflecting axes, and these are another type. Let me make this darker so you can actually see the frieze. But we have the same thing for n-gons as well. So if we let f be, so if we have an n-gon where n is even, then we have two types of reflections, ones that bisect sides and ones that bisect angles. And then if n is odd, we have one type of reflection, ones that just go through one side and one angle. If f is this central axis that's vertical, then these blue axes, when n is even, are r to the 2k f, and the green ones, the ones that go through the corners, are r to the 2k plus 1 f. So odd powers of r versus even powers of r. Here is a visual reason why each of these two types of reflections forms a conjugacy class in dn when n is even. So here's a hexagon, and this picture is going to be like the frieze group one in the previous slide, except instead of going on forever in both directions, it wraps around after 6 edges. So let's let f be the reflection about a central axis, and suppose that we want to reflect about a different axis that has the same type, this one here, say. Well, to do that, we first need to rotate this hexagon to get these blue triangles back in central position, and then we reflect about that central axis, and now we just have to rotate back, that is go clockwise, which is r inverse, to get back to here, and the net effect is that reflection. So r squared f equals rf r inverse. Here's the analogous picture for the so-called corner bisecting axes. So for this one, notice how I've colored the triangles on top a little bit darker, and suppose that I want to reflect about this the x-axis, and I want to compare that to the reflection about this axis here, which is RF. So suppose that this is our so-called home or central axis. So first we need to rotate this back into position, and now we can reflect about this axis, and we get this, and then we just have to rotate it back. That is, so this is R, and this direction is R inverse to get these things back here. And the net result is that we have reflected about, notice, this x-axis. So what do you think the conjugacy classes of a reflection is in dn when n is odd? We'll answer that later if you don't already see the answer. So now we're going to look at verifying the conjugacy classes algebraically. And we will start with D6 as a motivating example. The center of D6 is just the identity and the 180 rotation. So these are the only elements in size 1 conjugacy classes. The only two elements of order 6 are R and its inverse, which is R to the 5th. These are not central, so they have to be in conjugacy classes of size bigger than 1, but these are the only elements of order 6, so they have to be together. Similarly, the only two elements of order 3 are R squared and R to the 4th. They are not central, so they are in conjugacy classes of size bigger than 1, so they also have to be together. Finally, let's consider the reflections. Let's take one, R to the I, F. We need to consider two cases. What if we conjugate by a rotation or by a reflection? So let's start with conjugating by a rotation, R to the J. So here that is. And now notice that we have F R to the minus J here, and we can swap the order of these if we negate the exponent. So if we write R to the positive J times F. And now we can combine exponents and write this as R to the I plus 2J times F. And notice that I plus 2J has the same parity as I, because 2J is even. And if we're doing things mod 6, then it's still going to have the same parity, mod 6. So in other words, we don't change the parity of the exponent by conjugating by a rotation. And now I'll show you that we also don't change it if we conjugate by a reflection. So let's conjugate by R to the JF. So this reduces down to this right here. Notice we have an F squared. Again, the inverse of R to the J times F is F inverse, or F, times R to the minus J. So these cancel. So now we have R to the positive J times F R to the I minus J. And so now we can, once again, we can swap the F and the R by changing the sign of the exponent. So now we have R to the J minus I times F. So this is R to the minus I plus 2J. So if we're working mod 6, so the exponents are taking mod 6, I and minus I have the same parity, and if we add 2J to it, we also have the same parity. So once again, whether we conjugate by a rotation or a reflection, we do not change the parity of the exponent. Therefore, R to the IF and R to the KF are conjugate if and only if I and K have the same parity. So here is the partition of the 12 elements of D6 into conjugacy classes. Here is the cycle graph where I've color-coded them by conjugacy classes. So these two are the center. These are the so-called side bisecting reflections. So they look like this is F, R squared F, R to the 4th F. And then the green ones are the so-called angle bisecting reflections. Let me put F right here. Finally, it's worth interpreting this in terms of a Cayley graph. So let's start with F. And let's notice that if we do R, F, R inverse, see, so we get, so red, blue, red inverse, we get R to the squared, or we get R squared F. So in other words, if we conjugate by a rotation, we just move over by 2 notches. And because, by the regularity of this, it doesn't really matter if this is F or, if we conjugate really any of these things by R, we're going to just move over by 2. So let's check that. If we do R squared F R, that's going to be, sorry, R inverse. So that's going to be R. Now R squared F is red F, and R inverse is there. So by conjugating this element by R, we've just moved it over by 2. And notice how this is, we could also write this as R2, R squared F, R minus 2. So we could write this as R squared F, R minus 2. So in other words, conjugating by R just moves us around every 2. and we conjugate by RF, red. So let's just write this down. So RF, our inverse. So RF is red, blue. So if we first do red and then red, blue, and backwards red, you see how we move over by 2. And then similarly, we can write R cubed. Maybe I should write R cubed F, R cubed F, R inverse. I'll let you check that this is indeed R to the 5th F. So these 3 things are conjugate, and these 3 things are conjugate. I'll also let you check that if you conjugate any of these reflections by other reflections, that you get the same thing. So basically, if you have a reflection, then you have this extra F in here, and the F is going to, at one point, just take you out here, and then doing it again is going to take you back in the inner ring. We can now deduce the conjugacy classes of the subgroups of D6 just by knowing the conjugacy classes of the elements. Here are the subgroups of order 2. They are each generated by an element of order 2. R cubed is central, so if we conjugate by R or by F, we stay right there. Over here, we know that if we conjugate F by R, the element, then we get to R squared F. We do it again, we get to R to the 4th F, and then we get back to F. And then over here, if we conjugate RF by R, we get R cubed F, and then R to the 5th F, and then RF. So these form a conjugacy class, as do these. Now let's look up here. So RF is an element that is in only one subgroup of order 4. This is it. So if I tell you that I can move this element over here via conjugation, then what's the subgroup that's above it? Well, it's got to be the unique subgroup of order 4 that contains RF. So I call this the single parent property. I don't have it on a slide, but it's in my book, where if you know that 2 subgroups are conjugate and they each only have one parent of the same order, then those things have to be conjugate as well. So once again, if I can conjugate R cubed F to R to the 5th F, well, that means I can bring R cubed F over here. And well, there's only one subgroup of order 4 that contains R cubed F. So it's got to be the one that is above. If I can move this over here, its parent has to move there as well. So we know that these things have to be conjugate. And then this is a unicorn, so it's got to be normal. All the purple ones are unicorns. Watch my video on conjugation of subgroups if you don't know what a unicorn is. It is, yes, unique to my book. And here are index 2 subgroups, so those are normal and in size 1 conjugacy classes as well. So this little picture that these little arrows that I've done, we're going to do a lot more of this in chapter 5. So this is the beginnings of what I call an action diagram or an action graph. It's like a generalization of a Cayley graph where you remember in the beginning when we hit buttons and when we hit the R button or the F button, things moved around. That's what we're doing here. We just don't necessarily have a bijective correspondence between the group elements and the actual set that the group is acting on. So this is a bit of a preview. So I hope you stick around for chapter 5. Here is the subgroup diagram of D6. Remember, the subgroup diagram is formed by taking the subgroup lattice and collapsing the conjugacy classes into single nodes. So we have 3 conjugacy classes here that have size bigger than 1. So I did tell you how big they are. And this is not the normal subgroup diagram. I've obviously annotated each of these conjugacy classes with cycle graphs containing a representative from each conjugacy class. So notice down here, there's a fundamental difference between the subgroups over here that are generated by a side bisecting reflection and one over here that's generated by an angle bisecting reflection. And both of those are different from this one, which is generated by the 180 rotation. Now up here, well, let's go over here. So here are the 3 120, or the 120 rotations in the identity. Here are all rotations. And then we have here both of these. Let me just say these are both isomorphic to This is D3, this is D3, this of course is C6, this is V4, we'll get to that later. Both of these are what we get by, in this case, taking only the blue reflecting axes and the 120 rotations, and this is what we get by taking just the green axes and the 120 rotations. Now up here, notice if we take a blue axis and the orthogonal green axis, then we get a copy of the Klein 4 group, V4. So there are 3 of those, and there's really, if you squint your eyes, there's no structural difference between any pair of perpendicular or orthogonal axes, one blue and one green. Now that's why these 4 subgroups are conjugate. Let's now turn our attention to conjugacy classes in Dn when n is odd. We'll take n equals 5 and claim that all reflections are conjugate. This should be reasonable because all of these axes are basically the same structure as the rest of them. There's no side bisecting or angle bisecting anymore. We can see this on the Cayley graph by noticing that, well, the same thing we just did is if we start with f and we conjugate it by r, so we do r, f, r inverse, we get, let's see, r, f, r inverse, we get r squared f. And then if we do that again, so if we do r squared f, r inverse, so we do red, blue, red inverse, we get r to the 4th f. So in other words, conjugating by r just moves us around by 2, and notice that we do that again, and we get rf, then we get r cubed f. Maybe you can see that better down here. If you start with f and you conjugate by r, you get r squared f, and then by r again, r to the 4th f, and then r to the 6th s, which is r to the f, and then finally you get r cubed f, and then once again r to the 5th f, which is back to f. So these are all in a single conjugacy class. Here's a cycle graph. And here is the partition of the elements of D5 by conjugacy class. So all the reflections are together. There's only one element in the center. But now this is a little curious. There are 4 elements of order 5. R, r to the 4th, r squared, r cubed. So why are they not all conjugate? Well, the answer is because there's something structurally different about a 72-degree rotation than say a 144-degree rotation. Algebraically, well, if we just take, let's see what happens when we take r, and if we conjugate it by any rotation, we're going to get commutes with any powers of r. So let's just conjugate it by a reflection. So if we do f r f inverse, which is so let's check. That's f f r f inverse. That is r to the 4th. Maybe I should have done that with blue. Oh well. But now let's actually check. I claimed if we do conjugate it by any reflection, we get r to the 4th as well. So first of all, r doesn't commute with any reflection, so we know that if we conjugate it, we'll get a different rotation. The question is just which one. So let's take r, and let's do r to the I f times r to the I f inverse. This is r to the I f times r times f times r to the minus I. So once again, we can swap the order. So let's get these f's together somehow. So let's just pick, doesn't matter which, let's pick this, and let's write this as r to the I times r to the 4th, right? R to the 4th f, or r inverse f, times r to the negative I. So now both of these things are going to cancel, and you see what's going to happen. We get r to the I plus 4 minus I, which is r to the 4th. So if we conjugate a rotation by any reflection, we get its inverse, which is r to the minus 1. We will see that in any dihedral group, if you take any rotation that is not the identity or the 180, something that's not central, it will only be conjugate to its inverse. that is something that will be like a one-line proof once we learn about centralizers in the next lecture. So make sure you stick around for that one. Let's now turn our attention from the dihedral groups to the symmetric groups. Recall that we introduced cycle type back in chapter 2. Before we give the definition, let's see an example. There are 5 cycle types in S4. There's the identity element, then there's the 2 cycles, the 3 cycles, the 4 cycles, and then the product of 2 cycles. Notice that some of these are even and some of them are odd. For example, 2, 3, 4 is even because I can write that as 2, 3 times 2, 4. Recall that we are reading from left to right in this book. Formally, 2 elements in Sn have the same cycle type if, when written as a product of disjoint cycles, there are the same number of length k cycles for each k. It is a classic theorem. It's not too overly complicated, but very notationally messy, so we will skip it. Is that 2 elements G and H in Sn are conjugate if and only if they have the same cycle type. So what this is saying is that when you permute n things, it doesn't really matter how you label or number them. All that matters is what the cycle structure is. For example, the permutations in S5 fall into 7 cycle types and thus 7 conjugacy classes. Let's quickly go through and see how many of these there are. So there's one element there's one identity element. Then how many 2 cycles are there? There's 5 choose 2 ways to pick a 2 cycle, and that's it. So there's 10. What about 3 cycles? There are 5 choose 2 ways to pick the 2 elements that get excluded, and then once we have that, then we have 3 more elements, say 1, 2, 3, for example, and we can cyclically order them 2 different ways. So 5 choose 2 times 2 is 20. And I'm going to go through these a little bit quickly because this is not a combinatorics course. I'm just doing a combinatorics exercise along the way. What about 4 cycles? So we have 5 choices of what we can exclude. In this case, we exclude 5. And then every 4 cycle is determined by the, let's see, so we can always start with the lowest number remaining, let's say 1. And then every 5 cycle is determined by the remaining 3 digits. So we have 3 factorial or 6 ways to choose those. And so that is 5 times 6, which is, there are 30 4 cycles. What about cycles? 5 cycles. So we can always start with a 1 in a 5 cycle. And then there are 4 factorial ways, which is 24 ways, to permute or to pick the last 4 elements, and that uniquely determines the 5 cycle. Okay, what about products of 2 cycles? So we have 5 different ways that we can exclude one of these elements, and then once we have the 4 that are not excluded, we have I think 3 different ways that we can group them into pairs of 2. So in this case, 1 can get paired with 2, with 3, or with 4. So 5 times 3 equals 15. And finally, what about this one? Well, we have 5 choose 2 ways to pick the 2 cycle. And then we have sort of like what we have over here. If we have the remaining elements, in this case, 3, 4, 5, there are 2 ways we can cyclically order them. So that is 2. So 10 times 2 is 20. So let's check that these things actually add up to 120. This is the order of S5. And so we have, let's see, we have 20, 35, 45, 55, 59. One is 60, 70, 80, 90, plus 30 is 120. Indeed, we have all of the elements right here. The big idea is that conjugate permutations have the same structure. They are the same up to renumbering the actual things or digits that we are permuting. Let's see another commutative diagram involving visuals and conjugation for the symmetric group. So let's take S6, which is generated by a transposition I plus 1, and an n cycle. We'll take 2, 3, and 1, 2, 3, 4, 5, 6. Imagine that 6 people are sitting around a circular table, and we can say that people in positions or chairs 2 and 3 may swap seats at any time, and people can always cyclically rotate their seats. Do you agree that we can get any seating assignment from just these two? We've been over this in chapter 2. But let's now suppose that people in chairs 1 and 2, say Alice and Bob, want to switch seats. How do we achieve that? Well, we take everybody here and we say, let's move over one chair, so rotate counterclockwise. That moves Alice and Bob into swappable position. And then we swap them, A and B, and we fix everyone else. And then we rotate everybody back clockwise, which is our inverse. Notice that the net effect is that all these other 4 people did not change positions, and A and B swap places. So we say that 1, 2 is equal to R, 2, 3, R inverse. And this doesn't necessarily work. So this doesn't just work because we have this particular cycle, 1, 2, 3, 4, 5, 6. Any n cycle will work. The proof of the theorem in the previous slide that 2 permutations are conjugate if and only if they have the same cycle type is basically done by generalizing this argument and come up with a formula for what the element that conjugates one permutation to the other is. Again, I think the biggest challenge of this is just keeping track of the actual notation within the proof. Let's finish by partitioning the subgroup lattice of S4 into conjugacy classes from our knowledge of conjugacy classes of the elements of S4, just by inspection. So over here, we have the 3 cycles. We know that those are all conjugate to each other. By that so-called single parent property that I mentioned in the previous slide, if these are all conjugate and they all have one parent, then these have to be conjugate as well. Here are the 6 2 cycles. And so we know that these things are all conjugate to each other. And here are the products of 2 cycles. So down here we have like 1, 2 times 3, 4. Notice that these things generate a Klein force subgroup, which is a unicorn. It's got 4 parents, whereas these Klein force subgroups only have 3. So because these are all conjugate to each other and they all have a single V4 parent, then these things have to be conjugate as well. Again, if I can take this C2 to that C2, well then it's what subgroup is up here? Well, it's got to be the unique parent of this C2, so that has to go over there as well. Similarly, these C4s all have to be conjugate because, again, all of these C2s have a single parent. These D4s, also by the single parent property, have to be conjugate. This is actually a slightly stronger version than how I phrased it earlier. I said that there's a unique subgroup, a unique parent of a certain order, but I guess if they have different isomorphism types, then you don't ever have to worry about conjugating one of these to one of those. So these have to be conjugate by the single parent property. A4 is a unicorn. It's a unique subgroup of order 12. And of course, S4 and the trivial group are normal as well. Let me make one more comment. These C4s are, as I said, conjugate by the single parent property, but there's another reason they are as well. So there are 6 4 cycles in S4. For example, 1, 2, 3, 4. And then let's see, the square of this, 1, 2, 3, 4 squared is 1, 3, 2, 4. That's something that's down here. And then this thing cubed, 1, 2, 3, 4 cubed is its inverse, 1, 4, 3, 2. So each of these C4s has 2 4 cycles, and we know that all the 4 cycles are conjugate. So that means that I can conjugate a generator in here to not only its inverse, but also to all the other generators in here and their inverses as well. And I think I'm going to leave things there. In this lecture, we learned all about conjugacy classes in elements, but we have not seen something called the centralizer, which is going to be the topic of the next lecture, the last one of chapter 3. The centralizer is to conjugacy classes of elements what the normalizer is to conjugacy classes of subgroups. So recall that the size of a conjugacy class is the index of a normalizer if we're in subgroup world, but it's going to be the index of a centralizer if we're talking about elements. Both of these are special cases of the more general orbit stabilizer theorem. And having this tool at our disposal is going to be really helpful and will help us answer things that we could not do already or would take a lot more brute force. For example, we can almost immediately deduce that every rotation in Dn that's not central is conjugate only to its inverse. So there's really neat, really powerful theory coming up in the next lecture, and there's a bunch of really pretty pictures that illustrate it. So stay with us.